Welcome to the next video in a course in real analysis. This is lesson 4.2. We'll be doing exercises regarding soups and functions. So this, although it's going to try to get to the exercises as quickly as possible, will have a pretty large amount of kind of exposition about notation and definitions. In particular for the definition and notation of the image of a function, a bound on the function, partial application of a multivariable or especially a two-variable function, and corresponding notations for suprema. It will show that the supremum preserves function order, and it will end in a fairly challenging proof of the interchange of sups for a two-variable function. So first, let's focus on a single variable function. So if we have a poset A, and we have a function from x to y, then first we'll define the image of the function on x to just be the set of all values of the function for any possible input. So that's general, right? That doesn't require the poset. But if we do have that y is a subset of A, so that makes this a subset of a poset, then we can say what it means for the function to be bounded. The function, we say, is bounded if the image of the function is a bounded set. Now, if f is bounded, and I should perhaps also at this point add that x is not empty. So I guess it depends on whether or not you regard the empty set as a function, but one way or another, all we're really interested in is the case where the set x is non-empty. And so long as it is non-empty, then the image is non-empty. And then if it is further bounded, then we can talk about the supremum of the function. The supremum of the function will just be the supremum of its image. As a first exercise, and this should be quick and simple, suppose that you have some two functions, both defined on a shared domain going to a poset. So I'm still taking A to be a poset, X to be a non-empty set. And so f and g are two functions like this. And suppose further that for all values in the domain, f precedes g. Then prove that the sup of f is precedes the sup of g. And so I have given the exercise here. I will show my solution much later because I've got a lot of other things to demonstrate or explain here. Let's now move on to the concept of a two-variable function. And in particular, there are a few ways to think about, taking sups and so on. So first of all, consider where you fix a particular value of x or a particular value of y. So to begin with, imagine that we take a particular fixed value of the set x, which here we'll call x prime, right? That's the particular value inside the set big X. And now with that, and given that we already have this function from domain x cross y, so that's a two-variable function, right? It's got two inputs, one from the set x, the other from the set y. It returns values in a third set, perhaps. Then in any setting like this, we can define a single variable function, which has as its domain only the set y. And in particular, the value of this function on a given input y is the same thing that you would get if you went to your two-variable function and you give as its x-coordinate this thing that we chose as our fixed value together with whatever the input y is. So anyway, the sort of point here is that this is effectively partial application, right? This is sort of fixing the value of x and then getting as a result a single variable function of y. So of course, there's nothing special about x. We could repeat all of this by fixing y and getting a function of x. Now, as a very simple exercise, but just to get you working with some definitions and, to break up the presentation here, because, if I just drone on and on without giving you something to do, it can get really tedious. So here is a very simple exercise, but go ahead and I encourage you to do it. Show that if your two variable function is bounded above, then no matter what choice of x you take from the set x, the partial application is also bounded above. Now, if we take a fixed x prime and get our partial application function f(x prime), then we can talk about taking the supremum over that of that function, right? So just as we defined the sup of a one variable function, well, now that we have a two variable function, we could fix some particular x prime and take the sup of that function. Of course, likewise, we can do the same if we fix y prime and take the sup over all possible choices of x, basically. But the point of going through all of this, like, very technical definitions and stuff that maybe, somewhat overlaps with what you've seen in a discrete math class, and so maybe I am somewhat repeating previous lessons, but the point of doing that is that there is this subtle distinction, which is when we take a two variable function and we do not fix x prime, and so when we would like to still be able to define what we mean here. And so what I am writing here is the idea of not necessarily fixing the x coordinate, but still letting it vary. So if we do this, then this is in fact a function, right? It's not a fixed value, but rather a function of x, right? We're taking the supremum over all choices of y, but this for each x, right? If you fix an x, then we get this as the result, right? So once you fix x, then this is the value that you get. But the point here is that now, right, the notation is only slightly different, and the concepts and the vocabulary, everything is so similar. But keep in mind, it's worth understanding that that when we write it like this, we mean a function of x. X is now a variable, not a fixed value. And this equation tells you what the function is. For each input x, this is the output corresponding to x. And of course, we repeat all of this with, where we take the sup over x and get a function of y. And so now that we have these concepts all in place, we know that this, for example, is a function of y. Well, because it is a one variable function of y, we can then talk about taking its sup in the same way that we talk about taking the sup of any one variable function of y. And so that's what this double stacked sup notation on a two variable function means, is that we first take the sup over x, which gets you a function of y, and then you can take the sup over that function of y. So that's what this notation means. So I tried to be possibly too tedious in explaining this, but I thought it might help when we get to the following exercise. So suppose that we have a totally ordered set and a function from any two non-empty sets, x and y. So the domain is the product, the Cartesian product of x and y, non-empty set. And the image is this, or the range is this totally ordered set, ordered by pre-seq here. Show that you get the same thing no matter which order you take the supremum in. Okay, that is the final exercise for this exercise set. So if you're gonna solve the problems, please stop the video now, make your own solutions, and then compare with the solutions that I present in just a minute. Okay, for that first exercise, we've got two one variable functions, and we're going to assume that f pre-seq g on every possible input. We will then show that the supremum of f pre-seq the supremum of g. Now, as is common when you're proving something about, suprema and this inequality, it's always nice to have a nice simple proof by observing that if we're going to show that something that sup f pre-seqs anything, all we have to do is show that that anything is an upper bound on the set that this is taking the sup over. So that would be that effectively all we have to do is show that sup g is an upper bound on the set, which is the image of f. Now, how are we going to show that? Well, the way that kind of stands out to my mind is to attempt contradiction, to imagine that there is something that is bigger than sup g, right? There's a point in the image of f such that that point is strictly bigger than sup g, right? So that's an assumption for contradiction. Now we know from the sort of information that is given in the assumptions of the problem that immediately from that we can say that f of that x pre-seq g of that x. But then we have that sup g is not an upper bound on the image of g, right? But that just contradicts the definition of sup g. So there's the contradiction and the proof is complete. Okay, for an even easier exercise, we will suppose that our two variable function is bounded above, and we will pick any particular element out of the set x, and we will show that f partially applied to x is also bounded above. So let m be the element in the range such that f is bounded above by it. Now, by definition, what that means is no matter which two things you pick from x and y, that f of xy is pre-seq m. So that's just what it means for m to be a bound above the function. And now, if we then take any arbitrary choice of x and look at f partially applied to x, we want to show that this, as a function of y, is bounded above by something. I'm going to show that it is bounded above in particular by the same m as the one that bounds the entire function. And if you pick any choice of y out of the set, right, we want to show that the image of y for f partially applied to x, we want to show that that is bounded above by m, right? That's what it is to show that this one variable function is bounded above. Well, f partially applied to x inputting y, that's the same thing by definition as the two variable function on inputs x and y. We already knew that that is bounded above by m, and that is all we needed to show. Okay, on to the sort of, real reason, honestly, for even presenting all of this stuff was just to get to this, which will be a useful fact later on and not easy to prove. So, so the other exercises were mostly kind of warm up, but building up to this. So, okay, under all of these assumptions, let's first fix any choice of x prime in x, y prime in y. And we know that when we fix y prime and look at plugging in, right, evaluating this function on input x prime, that, taking the sup over the function where y prime is fixed, just means that this is an upper bound on the set of all image points. So this inequality just follows immediately, again, because this is an upper bound on the image and this is a point in the image. Now, I'm putting this up here so we can remember what we just showed. Now, as we go on, let's notice that it is very easy to observe, prove if you wanted to, that fixing y evaluating at x, or let's say fixing y prime evaluating at x prime is the same thing as fixing x prime and evaluating at y prime. So that gives me an equality for the left-hand side. Before doing anything with that, let's also say something that we can use for the right-hand side. Now, by definition, the sup of this, right, that is fixing y prime and taking the sup over all possible choices of x, so that is effectively the same thing as this right here. So now let's sort of perform this substitution where the left-hand side becomes, you know, what we said it was equivalent to, where we're now fixing x and evaluating at y prime. And over here, we're kind of just expanding the notation on the right-hand side. And now, since this inequality is true for each arbitrary y prime, right? Y prime was chosen arbitrarily. And so now we get that this is an inequality as functions, right? I mean, you know, basically all we're doing is saying, well, we were thinking of y prime as fixed, but since it is true for all fixed y prime, then it is also true by definition for these as functions of a variable y. And now the thing about this inequality holding for functions is that in exercise 1, we proved that when you have a single variable function and an inequality like this for your single variable function, then you can infer that the sup on the left-hand side precedes the sup of the thing on the right-hand side. So here we have it from exercise 1. We take the sup over the left-hand side, and we know that that must precede taking the sup. And notice, by the way, this is the same as the sup over all y. And I'm doing exactly the same thing over here, so that that follows from exercise 1. Now, at this point, we do a somewhat similar trick that we basically say, well, okay, so if this is true, but we picked x prime arbitrarily, right? So since x prime was chosen arbitrarily, then we could also regard this as a true statement about the function, right? Treat this as if it were a function of x rather than for a fixed x prime. This would be true for functions, and then where this right-hand side would have no variable because it is now just a specific number, but that then just means that this number is an upper bound on the image of this as a function. And so from that, we now know that because it's an upper bound, then when we relate it to the supremum, which, recall is the least upper bound, since it is an upper bound, then the supremum must precede any other upper bound, and we get exactly the inequality that we were trying to obtain. Of course, right, this gets us an inequality. What we were going for really was an equality. But I think it's easy to see that there's nothing special about x, there's nothing special about y. We could have done everything in the reverse order, so mutatis mutandis, exactly the same proof would get us the inequality with x's and y's swapped, and now that we have those two directions of the inequality, we get an equation. Okay, so that concludes the proof. Somewhat naturally, when we show a thing like that, with typically an upshot of something that says like the order doesn't matter, means that like kind of our notation reflects that we don't care about the order because you get the same thing no matter which order you write it in. So because of that, we will sometimes write the sup taken over all x and x, y and y to mean one or the other of this or that. And because of what we just showed, it doesn't matter which way you interpret it. And I'd like to end with an invitation to ask questions. So if you found anything in this video confusing or in related portions of the textbook, please leave a question in the comments. Try to make it as clear as you can. And if I can address it in the comments, I might. But if it is more involved, then I might make a video and include it in the playlist.